If you're doing any kind of serious game development, you're going to have to deal with state management. It might be the state of the player, the state of the world, the state of the enemies, and so on. If you don't manage that state well, then you can end up with an unmaintainable mess of code. The point of this video is to walk through a couple of different approaches for managing state so that you can see some different ways that it's done. And my particular example that I want to use is Space Invaders. So hopefully you're familiar with this game. There's this swarm of enemies and they move together to the left and then down and to the right and then down. So that'll be what I'm building up. And I've decided to build it pretty much from scratch so that you can see all the different steps. That means this video will probably get a little long, but here's an overview. And I'll leave in the video description some links so you can hop to different parts of the video. I'll start with setting up the project, and then we'll look at just kind of an ad hoc approach to managing the state. So nothing fancy, just doing what seems best at the time. Then we'll look into using enumerated types, and then I'll conclude by showing you how to use the state design pattern. Let's get into it. This project was created from the empty project template using Blueprint, and all I've done so far is connect it to Git for version control so that I can commit along the way in case I mess up I need to go back. So the first thing I'll do is I'll import my alien image, which I have in a to import folder here, and we'll rename that, and then we'll make that into a sprite. And let's go ahead and make a blueprint actor out of that as well. So I think what I'll do then is make a new blueprint class, and I'll be using paper 2D, so I'll go make a paper 2D actor. Oops, paper sprite actor, there it is. And we'll call that BP alien. And in here we can set the render component to be our sprite we just created. One other thing that we'll have to do eventually, so I might as well do it now, is to make this a movable sprite. So that should set up the alien. And while I'm here, I'm also going to go to the editor preferences and make sure that we're going to dock by default to the main window. That's what I prefer anyway. Okay, so that's enough that we can take a single alien and drop it in there. But what I'd like to do now is deal with this property of swarms of aliens. Let's look again at that Space Invader screenshot. It's pretty clear here from an object-oriented point of view that each one of these aliens is an actor, and that's what we just set up over in Unreal Engine. What might be less obvious is that the whole swarm itself can also be conceived of as an actor. In teaching game development, I've found that sometimes students have some trouble seeing this as a model because they think of a one-to-one relationship between a visible representation and an actor. But this is a really nice case where you can have this idea that the actor may be composite. It might be an aggregate of many other actors. So I'm going to use child actor components so that there's one swarm that has any number of child actors. That'll make it easy for me to manage the behavior of the swarm as one agent. Let's get back to the editor. Okay, so let's start in on that swarm. This will be an actor. We'll call it BP swarm. And what I'd like to do is, at design time, be able to specify the number of rows and the number of columns and the space between aliens. So if you haven't seen that before, this is a really nice feature of Unreal Engine. I'm going to handle that in the construction script, but I'll need a couple of variables to pull this off. So this will be the number of rows, which will be an integer. And I really want that to default to 1, and I'm not going to do any kind of fancy error checking here, so I'm just going to put in the minima there as 1. Let's duplicate that to make columns. And I'd like to put those both into a category called configuration. Good. And we'll make one more, which will be the spacing between the aliens. That can be a float, and also put that in the category. And from a little tinkering around I've done, I think 150 is a good default there. For all of these, we'll make them instance editable. Okay, let's start with probably the easiest part is setting up a pair of loops to go through the rows and columns. So here's a for loop, and we'll have this go from 1 to the number of rows. and then we'll nest there another for loop that will go through the columns, starting at 1. Okay, so this will run rows times columns times, right? Making sort of a grid is my idea. Let's try adding a child actor component here. And if we click on this node, we can set the child actor class over here, and this will be BP Alien. Good. Let's hook these up. Now, I'm not doing anything with the spacing right now. I'm leaving the relative transform blank, but that's already enough that we can kind of tinker with it and see if this is working. So if we drop a swarm here, then we can see there is one alien. And if we use the outliner, we can see indeed there's a swarm and it has a child, which is one alien. But if I go over here and say 2 rows and 2 columns, now there's 4 aliens. Now remember, I haven't changed the transform at all, so they're actually all in the same space. But we can see that already we have the right number of them being created. All we have to do is spread them apart. So back over in the swarm, I think the easiest way to do this is going to be to compute ahead of time the total width and height of the area that I'm going to populate with these aliens. So let's make a new local variable called width. And that's already a float, good. So we can set the width to be the, let's see, that'll be the number of columns minus 1 times the spacing. Right, we have to say minus 1 because the spacing is only between the columns. But of course, this is a little awkward. What I'd like to do instead is replace that with a math expression. So this will be columns minus 1 times spacing. There, I think it's a little easier to read. And we'll do a similar thing for height. So that will be rows minus 1 times spacing. Good. Okay. Now what those will let me do is map from my range 1 to rows and 1 to columns into this actual space, into width and height. So here, what we'll do is we'll use a map range, and I usually default to unclamped. Let's see, let's do rows first. So that's our value. We have this conversion node we've got to deal with. And my range is starting from 1 and going to the number of rows. Again, we'll need a conversion. Good. So that's my initial range, right, at the indices of this loop. And my out range is going to be, let's see, these are the rows, so this will be height. So what I'll do is I'll say height divided by 2. Oops. That's half the height to negative half the height. Good. And then we'll do a similar thing with the columns. Although, let's go ahead and just plug that in and see what we have so far. So if that's the range, let's open this up. We're really just dealing with the transform location. Rows, so that's Z. So if we hop over here and take a look, see right away we have these 2. We can make 3 rows instead. And we're still getting the right number of aliens, but the columns aren't spread out. So let's go ahead and do that. And that'll be a very similar kind of logic here. So we'll just slide that over and make another one. This times it's this index. And in range from 1 to columns. And then we have width divided by 2. There. And duplicate that. and get the negative. And plug that into our x. That's a little sloppy, but good enough for now. All right, so here's 3 rows and 2 columns. If we wanted 4 rows and 5 columns, there, that looks pretty good. I'm happy with that. As long as I'm in here, I think I'd also like to set up this level too. Now right now, if we play, we actually possess the default pawn, but we don't want to deal with the default pawn here. So I'm going to make a new game mode. We'll call it BP game mode. And in here, we'll just remove the pawn entirely. That should be all we need there. So now I can do the project settings under maps and modes, make sure I'm using that game mode. And here, let's clean this up a little bit. Really, all I want is my swarm and a camera, so I'm going to just start cutting everything else out. And let's set that to the origin just for convenience. And drop in a camera. All right, and I'd like to use an orthographic projection here. There, that looks pretty good. Yeah, I'm happy with that. Maybe we'll drop this camera down just a little bit. There. And we'll call this the default map. And again, over in the project settings, make sure we specify that under maps and modes. Good. Okay, so that's a good amount of setup. Now we can start dealing with the problem of having the swarm move left and right and downward. There's a couple of ways we could approach this. We could just set absolute barriers as numeric constants. We could say something like, don't let the swarm move left of 700 or something. But what I'd like to do is do it with barriers that I drop into the level, which means that from inside the editor I can move those around. Let me show you what I mean. I can grab a box trigger, and again I'll just start that at the origin and then pull it out. Actually, I think I want it about negative 700, and then we'll just stretch it way out this way. That looks good. And now I'll duplicate that over to positive 700. And let me just peek and make sure these are coplanar. Yeah, good. My idea here is we'll move the whole swarm over, and when it runs into the trigger, we'll change directions. Okay, let's try that. In the swarm, on tick, we can say get all the child actors and go through all of them. And we'll just give each one a world offset. Now, just to make sure all the pieces are working, let me just stick in a constant value here. Uh-oh. Let's see what's wrong here. Camera is looking in the right direction. Oh, I haven't possessed the camera, that's all, or auto-activated the camera. Here we are. Yes. Good. All right, so now they're moving right through that trigger because we haven't done anything with the trigger. Let's go ahead and do that. So I think the easiest way to do this is when, well, keep in mind we can't use event actor begin overlap because that checks for this actor itself, but it's not this actor that's overlapping anything, it's the child actors. So we don't need this. Instead, when the game starts, we can watch all of the child actors to see when they overlap. So I'll show you what I mean. Remember, the construction script has already run at this point, and it's stable, right? We have the right number of aliens at the time begin play is called, which means there's no danger here. We'll just loop through all of those child actors. And for each one, we can bind to on begin overlap. So we can say when any one of these children overlaps something, we'll activate this event. There, that's good. And again, just a sanity check. It's no harm just dropping in a print string here to make sure it's working. Sure, that's right where it hits there. Good. Okay, so now that's all the setup we need. We're now at a point where we can start dealing with the management of the state of moving the whole swarm left, right, and down. I'm going to start with just a horizontal movement because you got to start somewhere. So what I can do is say when this overlap event happens, we need to change direction, but that's after processing all these, because keep in mind what's happening here. Just for clarity, let me make these things not hidden in the game. When they overlap, it's going to be the whole column that overlaps all at once. So we can't just immediately change directions. We need to track that that overlap has happened. So here's how we can do that. Let's have another variable here. We'll call it did overlap this tick. And that's a Boolean. And by default, it should be false. That's good. If we get any kind of overlap, we'll just set that to true. But at the beginning of tick, we'll set it to false. Okay, so now we have to deal with are we going left or are we going right? So we'll say another Boolean here, which will start as true. Let's see, if we split this now, it's really just the sign of this that matters. Although I'd like to pull out, I think, speed as its own variable as well, because I don't really like putting the constants in here. So speed will be a float, and we will have that start as 5. So now what we can do is do something like a select node to ask the question, are we moving left? So if we're moving left, we're going to take speed and negate it. And otherwise, we can use positive speed. Okay, so what do we have so far? We go through all the children, we move them in the direction we should go. Once we're done with that, we can ask the question, did we overlap this tick? If so, toggle this variable. There, I think that looks about right. Let's try it out. Yeah. Okay. So the next step is to get the downward movement working. So let's just approach that again in this ad hoc way. And ad hoc, of course, doesn't mean bad necessarily, it just means what seems like the right thing at the time. So since we used is left Boolean here, let's add another one, and we'll call it is moving down. Maybe I should just say is down. Maybe I should rename the other one. Let's do that. There, good. Okay, so now how does the logic change? When we hit an overlap, it's true that we hit an overlap this tick. We're no longer moving left, but also we are moving down. Now, what I want to do with downward movement is have it go a specific distance, because obviously I can't, well, I suppose I could drop in a bunch of barriers and see when I hit those, but that seems awkward. So let's add a new bit of configuration, which will be the vertical distance. That's how far down we move. and we'll start that at about 50. And I'll need to be accumulating how far I actually moved down. And that'll, of course, start at 0. So what we can say then is, well, let's worry about the change here first, because this has to change. We'll need another select if we follow the same pattern, and ask, are we moving down? If we're not moving down, go ahead and use this. But otherwise, but we can't get away with just x, because now it's actually the whole location. So let's see, these are going to break in funny ways. There. If we're moving down, then we simply go down by the speed in the z direction. Well, see, down would be negative speed, so we'll get that and negate it. Otherwise, now this, let's see, well, what we could do is split that and take the original node here and just plug that into the x value. Yeah, so if we're moving down, then we have negative z. Otherwise, we're going to have either positive or negative x based on that is moving left state variable. Okay, that looks good. This is checking for overlap. Now we can say if there was an overlap, we should be moving down. Let's see where we're at. We hit that and we go down. And so right now we're not actually checking to see if we've moved down far enough, but this is good. This is a step in the right direction. So we can say after we're done moving all these guys around, let's set this to be whatever it was plus the speed. Oops. Then we can ask the question, well, I guess we may as well do that here, because we can then say, is this value greater than or equal to vertical distance? Let's see, if that's the case, then we're done moving down. Okay. Otherwise, but that's not quite right, because we actually need to check here if we're moving down, because all of these things will only do if we're moving down. If we're not moving down, then we have to check for the overlap. Let's see. So in the case where we're moving down, add these up, and if we've maxed out, then we set that. We should probably also then zero this back out. Okay, that might be it. Let's take a look. Hit the side, overlap, go down, overlap, go down. Good. Okay, so let's take a step back and look at what this code looks like. We have a couple of state variables. Did overlap, is moving down, is moving left. And we have this ad hoc management of state where it's kind of hard to look at any place within here and know really what it means. Notice that is moving down actually has a sort of priority over is moving left. That's not well communicated here. It's checked first here, so it has a priority, but the code doesn't really shout that out. It's not real obvious to the person reading and maintaining this how that's going to work. So we've seen that we can make this work, but I think this also motivates the need for something that has a little bit more grace. Before I move on, I want to quickly commit this. And again, that helps us out in case we mess something up and need to get back to this point. Now let's look at this from the perspective of a state machine. Let's go back to our diagram. So we know that in the game, this whole swarm will be moving left or moving down or moving right. So a naive interpretation of that might be to create a state machine something like this. We have a moving left state, and from there we can move down. Or if we're moving right, we can move down. The problem is, if we're in the moving down state, uh, where do we go from there? Do we start moving left or do we start moving right? There are techniques from computer science that can help us here, like push-down automata or hierarchical state machines, but I don't want to get into that. I want to stay with a simple state machine. So what I'm going to do is model this with 4 states. We start by moving left, and then we'll hit the barrier. Then we'll be going down the left side. When we're done with that, we go to the moving right state, and when we hit the right barrier, we are going down the right side. And from there, we return to moving left. So we have a very simple state machine, and we can model that explicitly. If you were to Google for Unreal Engine state machines or state machines in game programming, I'll bet you dollars to donuts that what you'll find is an explanation of how to use enumerated types to create a state machine. It's a very common technique, it's a very old technique, and that's the one we're going to move into now. So let me show you how that would look in Blueprint and Unreal Engine. Okay, so the first thing we're going to need here is an enumerated type. So under blueprints, we can make a new enumeration, and I'll call this eSwarm state. Now each one of those states that I showed you in that diagram is going to be a new value here in this enumerated type. So there'll be 4 of them, and they will be moving left, down left, moving right, down, whoops, down, right. Well, that looks downright pretty, doesn't it? Ah, sorry about that. Okay, let's get back to the swarm and look at how we can migrate our current implementation toward using this instead. One of the key pieces here is we'll introduce a new variable called state, and it will be of type swarm state. And notice it has a default value we can set here, and we'll keep that as moving left again. Now the idea here is anytime we are doing a state-dependent behavior, we'll check to see if we're in a state that cares about this. So here's one example. We actually only care about this begin overlap if we're in the moving left or moving right states. So let me throw this into a switch. And have it based on our current state. And we say we really only care about those in those 2 states. In the other states, if we're going down the side, overlaps don't matter for this. Okay, let's find the other places where we have state-dependent logic. How about all this stuff? Let's swap that out. We can once again use a select node, and this time we'll have it based on the value of our state. And the return value will be the delta location. So now we can say, let's handle this easy case first. If we're going down left or down right, then we just plug speed, it's actually negative speed, right, into z. Oops. And if we're moving left or moving right, when we're moving left, we're going negative in x, and when we're going right, we're going positive in x. Notice that when we split those nodes, it gets a little bit messy here, but fortunately, if you name your enumerated values right, then you can still see that these are in trios of x, y, z based on the current state. Okay, so what do we do after the loop, after we're completed? Let's see, let's just get this out of here for now. And we can say we'll drop into a switch on eSwarm state. Plug in the state. Good. Okay, so if we were moving left or moving right, those are the cases where we want to know if we had an overlap this tick. So that's this logic. And for simplicity, maybe we'll go ahead and just duplicate that for now. We can always factor it away. This means we were moving left and we hit a wall, so we will change the state to moving down on the left side. And if we were going right, then now we are moving down on the right side. So that handles all of this state management. Okay, what if we were going down on the left or down on the right? Well, those are the cases here where we need to actually accumulate vertical distance. Good. So let's take, I think what I want to do is just collapse this to a function, and we'll call this accumulate vertical distance. Oh, I suppose we do actually need that output there. There. I think that'll allow us to have a little bit less of a mess here. Because we can say if we're moving down left, we will accumulate vertical distance. Then we can ask this question. I suppose that could be part of the function too. Or I could stick it in a macro. I think I'm getting my cart before my horse. Let me Control Z out of there and just start by copying and pasting, because I can always replace these other things. This is the important part. All right. If we're going down left, add up the distance, check to see if we've exceeded the value we need. If so, reset that value and set the state. We would be moving right then after this. This is where we're going down across the left side. Okay. And for now, let's just copy that and paste it down here. Except now, this is moving left, because that's when we're going down the right-hand side. We've hit the accumulated distance, and we get out. Good. Now, yeah, that is pretty ugly, so maybe we do want to collapse that to a macro. Let's go ahead and do it. It won't take very long. We'll take this whole thing, we'll collapse to a macro, and we'll call this process vertical distance. And what I want to do here is make that into an input on it. So this will be a new input, which would be the next state. And we'll plug that in over here. Right, so it's a state to go to if all that other stuff is done. That's a little ugly, but we're going to be okay. So back over here, we'll process this. If we're coming out of down left, then we're going to go moving right. Similarly, then we can replace that with the call to this macro and have that go to moving left. Okay, good. There's probably too much refactoring before testing, but the network of nodes is bothering me. So here we go. That looks pretty good. Let's take a step back and look at this. What do we have now? We don't need is moving down. We don't need is moving left. We still need did overlap this tick, because that has to sort of store the value here for the overlap and then get processed in the states that handle moving left and right. But hopefully you'll agree that this is a bit cleaner. It's probably much more obvious too that if we wanted to add more states, maybe there's a chance that the swarm goes into a state where it moves in little circles or something. Hopefully it's pretty clear that you can add one and then handle the state-specific logic um, well in a much more elegant way that keeps it maintainable. Let's go ahead and save and commit this again, just in case we mess something up later and want to go back to it. This would be implement the enumerated type solution. Good. So let's talk for a moment about the problems with this approach. And I already alluded to one of them. So this variable did overlap this tick. Well, we need that only in some of the states, but it still sort of takes up space, cognitive space. So I'm not worried about how much memory it uses up in the computer. I'm worried about how much memory it uses up in my head. Um, if I'm focused on the moving up and down, for example, then I care about accumulated vertical distance. But I don't care about did overlap this tick. If I'm moving left and right, I care about did overlap this tick, but not accumulated vertical distance. But this blueprint, this class, still has to deal with both of those all the time. So there's a sense in which, even though we have the state-specific logic being handled in a nice way, it's still kind of leaky, right? The ideas of those states are polluting into the rest of the space. This is one of the major problems that can be solved by the state design pattern, which comes out of the object-oriented design patterns movement. Let's start moving toward that solution. And the key thing to remember is that what we want to do is encapsulate each state into its own object. But before I get into that, let's take another look at that state diagram real quick. All right, here are my four states. Now, it would be perfectly viable to create four different classes, each one representing one of these states. But something that I'm sure you can notice here is that moving left and moving right are almost identical in their implementation. The only difference is the sign of the X. Down left and down right are also almost identical. The only difference is which state do they go to next. So rather than use four classes, I'm going to create two, one of them for horizontal movement and one of them for vertical movement. Let's drop in and see what that looks like. Okay, my first step is going to be to make an abstract state. So I'll make that in Blueprint, and we'll make it an object. Not an actor, not a pawn, just an object. And we'll call it BP swarm state. The idea here is to delegate all of the state-specific operations to one of these objects, or more specifically, an instance of a subclass of this class. So we're going to need a function that handles the overlap, and we're going to need a function to handle the tick. Let me go on a little aside here. I like programming in Java in part because it has a really robust system of inner classes, and that gives you very nice control over the scope of objects. In Blueprint, we don't have that level of elegance, and so we really need to pass along the stateful thing into its states. So let's see what that looks like here. We just need to add the swarm as an argument. Okay, so now both process overlap and update are taking swarms as parameters. Here's another neat idea in this design pattern. We can set up both of these functions so that they can return the new state that we're going into. Actually, process overlap won't need that, but update can. As a result of updating, we might transition into a new state. So we will do this, have it return a swarm state called new state. Now, most of the time, I'm going to expect this to return nil or null or none, whatever you want to call this, right? No value. But if it returns a new object, then I know that that's going to be my new state. Okay. Let's go ahead and create now those horizontal and vertical states. Let me point out too, if we were doing this in C++, we could pull some tricks with the static keyword so that we wouldn't have to create new ones each time. We could reuse instances, but I'm not worried about that. We can make this work in Blueprint. Let's see, we'll make a new child, and we'll call it BP horizontal movement state. And we'll go ahead and just stub in the other one too, BP vertical movement state. Let's start with horizontal. Okay. In this state, when there's an overlap, I need to record that. And that should be false by default, but when we get an overlap, we'll set that to true. Now, of course, keep in mind, if we actually finished a Space Invaders game, we'd have to check for other kinds of overlap, like getting shot by projectiles. This is just a simplifying assumption here. Actually, I know the parent isn't doing anything, so I'm going to go ahead and just, in the interest of simplicity, remove that. All right, so if there's an overlap, we set that. Now, in the override update method, good, same kind of logic here. I'm just going to cut that out. We can always add it back in if we needed it later. What do we do on update? Well, we have to get the child actors and iterate through them. And for each one, we'll add that world offset. Okay, so are we going left or right? That's something that this object needs to know. So let's just add another variable called isLeft, and we can make that expose on spawn. That way, when we instantiate one of these state objects, it'll know if it's left or right. Because where that matters is right here. Based on whether we're left or not, we either use the speed or the negative speed. Yeah, that's fine. So if we're going left, then this is going to be negated. That looks good. Great. So after we move, then we can say if we overlapped this tick, then we have to switch into a moving downward state. So that's where we can create a new object from class, construct object from class rather. This will be a vertical movement state. And we may as well just use the swarm as the outer here. Okay, so one of the things we'll have to do is hop over to the vertical, because it needs to know if it's the left or the right also. So we'll just copy the same idea here and say this is expose on spawn variable. All right, and here we will refresh. Okay, so if we were moving left horizontally, then we're going down the left side. That means we can just plug that in that way and then return that as the new state. All right, good. Let's check out vertical movement. Vertical movement, we don't even need to override process overlap, so we'll just go to update. What do we need to do? Get all the children and iterate through them. We're going to add the world offset. And now this will always be the speed negated, oops, in Z. Good. Now this state, vertical movement, is going to be accumulating. Now remember, every time we're going into a vertical state, we're actually creating a new instance here, so we don't have to worry about resetting this. It should always start off at 0. So when this is done, we will set accumulated vertical distance to be the previous distance plus this speed. Then we can ask, is this always greater than or equal to? And now again we have to peek into the swarm and say, what is that vertical threshold there? Maybe that deserves a slightly better name, but it's okay for now. All right. Did we hit that threshold? If so, we need to switch to one of the horizontal states. Okay, if we were going down the left side, then we're moving right, which means we have to get this and toggle it. And then plug that in. And again, we may as well use the swarm as the outer here. And then we return it. Okay, so that should be all the logic for horizontal movement and vertical movement. Now we can go back into the swarm and refactor this so that it's using those states instead. First thing we can do actually is get rid of all of that. That's nice. And that. And this. We'll change the type of this variable from the enumerated value to the actual class type. That's fine. Good. Oops. That's odd. There, that's better. Okay. We need to give it a default value, so let's do that in begin play. Probably easiest just to pull that out and do that first. So we will set this state to be we'll start with a moving left state. So this will be horizontal, moving left, and again we'll use the swarm itself as the outer. Okay, so that makes sure that when we get started we have a valid state. What do we do when there's an overlap? We just tell the state. And we'll send along the swarm as a parameter. Although I don't think right now we're using it, so we could probably factor that out if we wanted to, but that's okay. Similar thing here. On tick, what do we do? Well, we tell the state. Self. Good. Now the trick, of course, with update is it might return to us the new state we want to transition into. So we can say if this is valid, right, which is like asking whether or not it's null. If so, then this becomes our new state. Oops. And we'll just use some reroute nodes here to make this a little bit more pleasing to see. Okay. Let's try it. Moving left, down, right, down. That looks pretty good. All right, let's review that code again. What do we have now? In the swarm, which is the stateful object, it simply delegates any state-dependent logic to the state. We've really simplified this guy. In fact, let's see, what can we eliminate? We can get rid of this variable. It is in use. I don't think that's true. Delete it. We can get rid of did overlap this tick. Good. In fact, we can get rid of that enumerated type as well. That's fine. Delete. Okay. So Undeniably, this got much simpler, right? This is very simple to handle. Let's look at those two states. Horizontal movement. It needs to know whether or not there was an overlap. It needs to know if it's going left or right. And so it encapsulates that within itself. If there was a problem with horizontal movement, we know exactly where to go. Vertical movement. It's the only state that cares about accumulated vertical distance, so that is encapsulated in here. That's really nice. Again, if vertical movement is broken, we know right where to change it. Now, if we wanted to add new states, what do we need to do? Well, really all we have to do is make a new subclass of our abstract state, right, BP swarm state, override the methods that we need, implement the new state, and then the only other changes we have to make are to the ones that depend on it. So if horizontal movement had to go to somewhere else, like circular movement state, then we'd change that state as well. So we have two pieces here. One is each state class encapsulates the logic of that state. And also, the fact that a state transitions to another state is known by the source state. Again, we can look at that visually in my diagram. So in each one of these states, they encapsulate the logic and they know where they go to. So if we wanted to add some new ones, we could do that pretty easily. So that's our introduction to state management. We took an ad hoc approach, which from my experience is pretty familiar. I see a lot of people writing code like that. There is the enumerated value approach, which is much more elegant, but still can lead to a lot of mess. And then there's the state design pattern, which was really introduced by people doing serious object-oriented software engineering to manage these complex states. I hope you found this useful. I hope it gives you some stuff to think about as you're trying to create some innovative games and also learn some cool computer science concepts. Happy programming.